Hey, welcome back. This is College Algebra 1610. Today we want to work with U substitutions, integration by substitution. It's 5.5. And all it really is kind of a method for reversing the chain rule, I would kind of put it at. So it's the chain rule kind of issue plus some other kind of some other issues that pop up when you're doing these integrals. So for example, before like f of x maybe equaled something like sine of x squared, and then when you took its derivative, what you end up is a product of two things, right? So it'd be cosine of x squared times 2x. Right? So now you'll be expected to find the antiderivative of these composites. So, for example, x times cosine of x squared dx. And kind of the trouble is it won't exactly be the derivative of, sine of x squared. It's kind of missing a constant here. So we'll do this kind of technique called a U substitution. So let u be x squared, and then du is going to be 2x dx. And then we could solve for dx and do some substitutions. Okay, so I can rewrite this thing as x times cosine of u times du over 2x. And then I can factor out a constant of 1/2. The x's divide out. And I have just the integral of cosine u du. And then, of course, the integral of cosine u is sine u. And then you can back substitute, and you have your answer. Okay? And, of course, you can go ahead and, for example, take that thing, f of x equals 1/2 sine of x squared plus c. Just take its derivative, f prime of x, and you should get back to the end sides of this integral here. Okay. So let's see if we get that. So it's 1/2 cosine of x squared times the derivative of x squared, which is 2x. The derivative of c is just 0. So we end up with 1/2 times 2x is just x, and then cosine of x squared. Yeah. So yeah, we're going to give you a method for basically reversing the chain rule, but there'll be other kind of cases that we can use this process for as well. Okay, so let's dive right in and maybe take a look at some of these problems. So for example, it used to be example number 3 in the book, but we'll just call it an example. So we have tan squared x times secant squared x dx. Okay. We kind of rewrite it is tan x squared times secant squared x dx. Okay, so you're looking to make a u sub for something such that the derivative of that something is floating about inside the integral, right? So, for example, if I let u equal tan x, the derivative of tan is sitting right here. You have to know the derivatives pretty well. Okay, so derivative of tan is secant squared, if you did not know that. So u equals tan x, and then du, and I take the derivative in the differential form. Du is secant squared x dx. Okay, and just there alone, I can kind of do my substitutions and simplify this integral. Okay, so if I let tan be u, I end up with u squared, and then so I'm doing just two substitutions here. One into this expression, which I just did, and then this other stuff, secant squared x dx, well, hey, that's just du. Okay, so you get du, and then you can integrate u cubed over 3 plus c, and then back sub. So u was tan x, so I get tan x cubed all over 3 plus c. Let's get another one. The integral of x squared times the square root of x cubed plus 1 dx. And I could see the derivative of x cubed plus 1 is kind of sitting in front. So I'm going to say let u be x cubed plus 1. And then I can get the derivative of u in differential form. Du is 3x squared dx. And then what I do is solve for dx. Okay, I mean, there's other ways to do it. I'll show you sort of the other way right now. You can kind of cheat a little bit to get that 3x squared dx, right? So if you rearrange things a bit, you have, the x cubed plus 1 times 3x squared times dx. And I cheated a little by kind of including that x squared. I just used the commutator property to move the x squared over, but then where did that 3 come from, right? Well, you can make it work out by just plopping in a 1/3 as well, because 1/3 times 3 is just 1, and you can multiply anything by 1 and not change it. And then you can factor out the 1/3, and you end up with the square root of u, basically, times du again. Okay. So in this case, we have then 1/3 integral u 1/2 du. Okay, so I just substituted in again. So u is sitting right here. The du is right there. This is du. Okay, and then I can integrate this thing. So I get 1/3 u to now the 3/2 times 2/3 plus c. And then if you begin in x, you have to end in x. So you need to back substitute and get 2/9 times x cubed plus 1 to the 3/2 plus c. Okay. Okay. So that's the idea behind integration with changes of variables or u substitutions. Let's make it a little more concrete now. The u sub, and look at kind of a bunch of problems. Right? Okay. In the book, I think the reading is a little bit misleading. The reading is misleading because some of the examples aren't exactly u subs in the traditional sense. They know what's coming around the corner, and they're trying to kind of give you a heads up. But the general method for u subs is kind of what I'm giving you right here. So let's take a look. And this method will basically work for any of these integrals from like 15 to whatever. Okay, so let's take a look here. Without further ado, let's look at some examples. Okay, so example t times the square root of t squared plus 2 dt. Okay, usually you want to make your u sub something inside parentheses or a radical or something. So this stuff right here would be a good guess. So u equals t squared plus 2. You certainly wouldn't want to try the square root of t squared plus 2, because that would kind of snowball your expression. You get all these weird radicals all over the place. It'd just be a nightmare. And the main goal of a u sub is to reduce symbols. Okay, so you'll begin with an expression with a lot of symbols in it, and a u sub will reduce numbers. And that's how the computer programs were first programmed to evaluate integrals. They would basically do a substitution and then count up the number of symbols, and if that number of symbols was reduced compared to the original number of symbols in the integral, then that was a good u sub, and the computer would chug away in that direction. Okay, so it really has okay, so anyways, get the derivative of that in differential form, so that would just be 2t dt. And then I could see it there, but rather than having the guess like I did in the last one and say, oh, I'm going to multiply by 1/3 and 3 and all that jazz, what I'm going to do instead is solve for dt. Okay, so I'm going to divide both sides by 2t, and so dt is equal to du over 2t. Okay, and this is all my u sub material. Okay, so now I do subs. Okay, so I have t times the square root of u times dt, which is now du over 2t. Okay, and you should see all the t stuff go away. If the t stuff doesn't go away, you screwed up, or you need to use a different u sub. Okay, because you won't be able to go forward. It's a gate. to open the gate, all the t material must go away. So anyways, yeah, the t's do cancel. There's a fraction of 1/2. I mean, this is just a product of a bunch of things, right? So you could factor things out of it. So I can bring a 1/2 out in front, and then you're just left with u to the 1/2 du. Okay? And then that's an elementary integral you can integrate using the power rule. U to the 1/2 plus 2/2 is 3/2 times 2/3 plus c, and then simplify it, and back sub. 2 to the 3/2 plus c. Okay? Okay. Let's get a whole bunch of these, right? So we got another one. The integral of 5x times the cube root of 1 minus x squared dx. Okay, so u, again, I'm going to just make it whatever's inside the radical there. So 1 minus x squared. Du will be negative 2x dx. And then I'm going to solve for dx. So dx is negative du over 2x. Okay, so here we go. So I have the integral of 5x times the cube root of u, so that would just be u to the 1/3, times dx, which I'm doing this substitution. Dx is negative du over 2x. Okay. First thing I'm going to factor out any constants. Just get those out of the way because they're messy and they get all over the place. So there's a negative I can factor out. There's a 5, and then there's a 1/2. So negative 5/2. The x's cancel just like I need them to. If not, I would have had to try something else. And the integrand is just going to now be u to the 1/3 du. Okay, so we got negative 5/2. U to the 1/3 plus 3/3 is 4/3. And then times the reciprocal of 4/3 is 3/4. And then plus c. And then we end up with negative 15/8. And back subbing 1 minus x squared to the 4/3 plus c. Okay, let's look at some with some fractions floating about. So, example, integral of x squared all over parentheses 1 plus x cubed squared dx. Okay. So, again, just kind of go to inside the parentheses and let that be your u. And then du hopefully is floating about there in the integral. So du, derivative 1 is 0, derivative x cubed is 3x squared dx. Okay. And then go ahead and solve for dx. And then sub it into your integral. Okay. So this will be the integral of x squared all over u squared times dx, which is now du over 3x squared. Okay. We can factor out a 1/3. The x squares will cancel, and you have now u to the negative 2 du. 1/3 u now to the negative 1 divided by negative 1. Let's see. So negative 1 all over 3 times u plus c. Back subbing negative 1 all over 3 times 1 plus x cubed plus c. Okay, what else? Trig versions of these. Let's look at maybe 1 or 2 of those. Integral of 1 all over theta squared cosine of 1 over theta d theta. Okay. Okay, so this one's, again, I'm just going to let u be whatever's in the parentheses there. The derivative of theta to the negative 1 is negative theta to the negative 2 d theta, which is the same as negative 1 over theta squared d theta. As usual, I try to solve for d theta. D theta will be negative theta squared du. Just multiply both sides by negative theta squared. Then I'm going to do my subs. Okay, so this will be the integral of 1 over theta squared times cosine of u times d theta, which is now negative theta squared du. I can factor out a negative. The theta squares cancel. And then I just have cosine u du. And then you can integrate cosine, right? So this would be negative. Integral of cosine is sine. And then finally back sub. Let's look at the integral of cosine of 8x. Seems like an easy one, right? So you can almost guess what this is going to be. You know, it's 1/8 sine of 8x, but you could always do a u sub. It's not entirely clear that you need a u sub because there's not like a product of two things, right? So in these other ones, you always see one thing times another thing. So cosine of 1 over theta times 1 over theta squared. Here it's not really times, more a division. So this thing divided by this thing. Here it's this thing times this thing. Here it's this thing times this. So it doesn't really fit the mold, and that's going to happen. You're going to get these ones that don't fit the mold, but you can still use this kind of process. Okay, you could kind of take advantage of it. And here I'm going to let u equal 8x. Okay, just whatever's inside of cosine. So du is going to be 8 dx, and then you can solve for dx. dx is du over 8. So this is going to become the integral of cosine of u times dx, which is now du over 8. There's no issues with the variables canceling or anything like that. So long as the integral is completely in terms of u, we can integrate it. Sine u du. And then, of course, the integral of cosine is just sine. And then we could back sub. But you could probably have kind of done that one in your head, just doing educated kind of guessing, you know. So you know that the antiderivative cosine is sine, and then if you were to do a chain rule, you would have to multiply by 8. So instead of multiplying by 8, just divide by 8. I don't know. Let's try another one. We have this example. So the integral of e to the 7x times 7 dx. Okay, this one's kind of already there. I mean, automatically you would just say, okay, the integral is e to the 7x plus c. Let's do a u sub though and kind of make sure that's the case. So u would be the 7x part, and then the derivative of that 7 dx, and then solving for dx, you get du over 7. Okay. So if we didn't know the answer, we could still use the u sub to figure it out, right? So you'd have the integral of e to the u times 7 times du over 7. Okay, so then the 7's would cancel out, and you'd have to have the integral of e to the u du. And of course then that would just be e to the u plus c, and then you get back sub, and you get e to the 7x plus c. So what I'm trying to tell you is that I'm giving you a highly mechanical process, right? Something I can apply program into a computer. But at the end of the day, you can still just use your brain. You know, you could look at some of these and know the answer. Okay. Let's try another. I don't know. Here's a nasty looking one. We could try this one. Integral of e to the sine of pi x times cosine of pi x dx. Okay. All right, so I'm going to let my u be the exponent of e. So we got sine pi x. And then du will be cosine of pi x, and I have to do a chain rule in here, times the derivative of pi x, which is pi, and then dx. Right? So dx will end up being du all over pi cosine pi x. Right? And then I can do all my subs. So the integral of e to the u cosine pi x times dx, which is now du all over pi cosine pi x. I can factor out a 1 over pi. The cosine pi x's cancel, and I just have an integral of e to the u du. Okay, so that will be 1 over pi. The integral of e to the u is just e to the u. See, and then back sub. So you get 1 over pi e to the sine of pi x, and then plus c. Okay, so fairly simple, highly mechanical. Once you get the idea, you're not even going to think you're doing math. You're just pushing variables around. There's some weird cases, right? So we want to hit some of these weird cases that don't necessarily fit in the U substitution category in a traditional way. Okay, so I'll just call this section 3. The weird the non-traditional, I guess we could call it. So example, the integral of x times the square root of 2x minus 1 dx. Okay, so if you try your u sub, you're probably like try 2x minus 1, right? And then your du would be 2 dx, and then you get your dx is du over 2. And then you do your substitutions, and you're in trouble. Okay, so watch. X times the square root of u, and then dx is du over 2. Uh-oh. The x's didn't go away. I'm in trouble. Okay. Well, actually, not as much trouble as you may think. You can go back to here to this equation and get rid of the x. You can use that equation. Okay. So if you solve that equation for x, what do you get? Well, you get 2x equals u plus 1. Then you can divide by 2. U plus 1 over 2. Okay. And then use that to get rid of the x. So x will be u plus 1 all over 2, and then times u to the 1/2 times du over 2. You can factor out a 1/4 this time. You'd be left with the integral of u plus 1 times u to the 1/2 times du. And then you can distribute the u to the 1/2. So you end up with 1/4 integral u to the 3/2 plus u to the 1/2 du. Then this would be 1/4, and now I can integrate, right? Power rule. U to the 5/2 times 2/5 plus u to the 3/2 times 2/3 plus c, and then you still always have to back sub. Okay, so u is 2x minus 1. So this ends up being 1/4 times 2/5 times 2x minus 1 to the 5/2 plus 2/3 times 2x minus 1 to the 3/2 plus c, and then you could distribute your 1/4. So you get 1, the 4 and the 2 is 1/10 times 2x minus 1 to the 5/2 plus 1/6 times 2x minus 1 to the 3/2, and then plus c. Okay. Right. So these weird ones are weird, okay, for a reason. Okay, let's look at another weird one. Let's look at the sum in the book for fun. We have x all over 2x minus 1 square root of dx. Okay, so again, naively you think like, okay, I'm going to let u be 2x minus 1, then du will be 2 dx, and then dx will be du over 2, and again you're kind of stuck, right, because that x in the numerator won't go away. But never fear. Again, you could go ahead and just take this thing and solve it for x, right? So you go 2x equals u plus 1, and then divide both sides by 2. And you can remove x and kind of replace it. Let's rewrite it a little bit. So this is really x u to the negative 1/2 times du over 2. And then I'm replacing the x with u plus 1 all over 2 times u to the negative 1/2 times du over 2. You can factor out a 1/4. So I end up with the integral 1/4 times the integral of u plus 1 times u to the negative 1/2 du. And then you have to distribute. So you get 1/4 integral u, now it's the positive 1/2 plus u to the negative 1/2 du, and then you can do a power rule on that. All right, so this would be 1/4 u to now the 3/2 times 2/3. So it seems like the exact same problem I just did. Oh, it's a little different. Okay, plus u to the 1/2 times 2 plus c, and then you could distribute the 1/4. And of course, you get 1/6 and back sub as well to the 3/2 plus 1/2, something in the 1/2 plus c. What was that? 2x minus 1. Okay, great. So those are always weird. Okay, let's move on to doing changes of variables. So definite integrals, basically. So what section was that? 3. So section 4 then. Definite integrals. And there's 2 methods for doing these. Basically, first, you can change the limits. Change the limits of integration. Okay, so let's look at maybe 1 or 2 of those. Ready then. So example. We have the integral from -1 to 1 of x times x squared plus 1 cubed dx. Okay, so when I go to my u sub and I'm doing all that junk, so I have x squared plus 1 inside the parentheses, and du is 2x dx. So dx is du over 2x. And then you can kind of rewrite this. You know, I got x times u cubed times dx, which is du over 2x. You need all the x's to go away. You can factor out 1/2. You get u cubed, so that works. You also, though, when you're doing all this stuff, you want to do a change of variables using that u formula. Okay, so originally the integral goes from x equals -1 to x equals 1. Our new integral is going from u of x equals something to u of x equals something. And that x is just the x you see in the original integral. So you're going to go from u of -1 to u of +1. And the u formula is sitting right here in red. Okay, so you need to figure out u of 1. So if you plug 1 into there, you get 1 squared plus 1, which of course is just 1 plus 1, which is 2. And u of -1 is the same thing, right? It's 1 squared plus 1, which will equal 2. Okay, so we're going from now 2 to 2. Regardless, that's just going to be 0. Let's go ahead and figure it out. Kind of 1/2 times the integral of u cubed is u to the 4th over 4, and then we're evaluating from 2 to 2. So that's going to be 1/2 or 1/8 now, and then 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 is 16, 16, and then minus 16, which of course would just be 0. When you have functions that have certain types of behaviors, for example, this guy is an odd function, and you're integrating over a sort of symmetric interval. Okay, so if it's an odd function, it'll kind of look like this. I'm sure that's not what this graph looks like, but in general, that's kind of what you have. And what's happening is you're getting a negative area and then a positive area, and if the areas are the same, they'll cancel out with each other. Okay, and that's what happened here. So just as a side note then, when f of x is odd, and you have an integral from over some symmetric interval about the origin, and you're looking at the integral of this thing, it'll be 0. Okay. Likewise, when f of x is even, you can kind of split it into 2 separate pieces. So the picture this time, if you have an even function, it'll look the same on both sides, right? So a good example is just the upper hemisphere of a circle. So in order to figure out the area underneath the whole thing, all you need to do is figure out the area underneath half of it and then multiply it by 2. Okay? So when f of x is even, the integral from negative a to a of f of x dx will equal 2 times the integral from 0 to a of f of x dx. So a lot of times you'll see professors split the integral at 0 because it's easier to evaluate. So if you've been doing enough definite integrals, you know, sometimes when you have a 0 in the lower limit of the integral, everything kind of goes away on the second part of the difference when you're defining the antiderivative and you're evaluating using the fundamental theorem of calculus. Right? That big F of A is 0 if the bottom one's sometimes. Anyways, okay, so sorry, I got sidetracked there on that little. So let's get back to the change of limits and integration. So let's do another one of those. Sure, why not? So this example, kind of a nasty one. 1 to the 3 of e to the 3 over x all over x squared dx. Right? Okay, so first I'm going to let my u equal the exponent of the exponential 3 over x, which is the same as 3x to the negative 1. Du will be negative 3x to the negative 2 dx, which if you would rather is negative 3 over x squared dx. And then you could solve for dx. That'll just be negative x squared over 3 du. And then we can do our substitutions and make sure everything works before we worry about the limits on the integral. So I have e to the u all over x squared times negative x squared over 3 du. So it looks like everything's canceling nice. We can factor out a negative 1/3, and we're just left with e to the u du. Okay, so now I'm going to change my limits on my integral. So I need u of 3 and u of 1. Okay. So u of 3 will just be 3 over 1 or 3. 3 over 3, right? Because u is 3 over x. Okay, so u of 3 will be 3 over 3, which is 1. And then u of 1 will be 3 over 1, which will be 3. So we'll be going from 3 to 1 now. And then we evaluate, so negative 1/3. The antiderivative of e to the u is just e to the u. And then we're going 3, 1. So we'll have negative 1/3 times e to the 1 minus e to the 3rd. Okay, that'd be kind of the answer right there. Let's try the other method. Okay, so the other method, method 2, it's kind of my method of choice. I don't bother with the other method, but what you're going to do here is wait until the very end and then just change everything back in the terms of x and then go ahead and integrate. So wait until the end and back sub. Okay, let's take a look at one. So we have 1 or 2. Let's take a look at an example here. We have the integral from 1 to 9 of 1 all over the square root of x times 1 plus the square root of x squared. Okay, so we'll let u be 1 plus the square root of x, and then du will be the derivative of 1, 0. The derivative of square root of x is 1 over 2 root x dx. And then, of course, dx, solving for it, I'll get 2 square root x du. Let's see if we get rid of this stuff. So we have 1 all over square root of x times u squared times dx, which is now 2 root x du over 1 if you wish. And we get some nice cancellations. We can factor out a 2, and we're just going to be left with u to the negative 2 du. And then we now need the change. We're not going to change the limits this time. Okay, we're just going to wait until the very end and then do back substitutions. Okay, so go ahead and integrate that. So it'd be 2u now to the negative 1 divided by negative 1. I have to remind myself to evaluate. That'll be negative 2 all over u. And now back sub. Okay, so negative 2 all over 1 plus the square root of x from 1 to 9. Okay, so evaluating now, negative 2 over 1 plus the square root of 9 is 3, minus negative 2 over 1 plus the square root of 1 is 1, so 1 plus 1. So this will be negative 2 over 4 plus 2 over 2, which of course is negative 1 over 2 plus 2 over 2, which of course is just 1/2. Okay. Sure. Let's do one of these, one more of these, and then we'll look at one of the even function types that I was kind of going on about before. So let's try another one. Let's do a trig version, 0 to pi over 2 of cosine of 2x over 3 dx. Okay. So I'll do my u sub for 2x over 3. And then my du is just going to be 2/3 dx. And so my dx is 3/2 du. Okay, so I drop the limits on my integral. I'm just going to turn it into u, and then at the very end I'll back sub. Okay, so I got cosine of u times dx, which is 3/2 du. You can factor out the 3/2, get the integral of cosine u du. Antiderivative of cosine is sine u. I have to remind myself to evaluate. Back subbing now, 3/2 sine of 2x over 3. And then we're going from 0 to pi over 2. Okay, and then evaluating finally 3/2 sine of 2/3 times pi over 2 is the same as pi over 3. Minus 3/2 times sine of 0. And the sine of 0 is 0, so we don't have to worry about that part. 3/2 times radical 3 over 2 gives you what you got, 3√3 all over 4. Okay, let's look at one even function. So I don't know if I can. I don't know if I can find one. Where are they? Here's an even one. Okay. Example, negative 2 to 2 of x squared times x squared plus 1 dx. This guy's even. If you can't tell, the usual kind of spiel is, especially when you're dealing with polynomials, all you have to do is look at the exponents. And if they are all even exponents, then the function is even. But in general, what the test is, you plug in negative x for x, and if that equals f of x, then it's even. The odd test was if you plug in negative x and you get out negative f of x, then it's odd. Okay, so this guy I'm saying is even. Note, if you put in negative x for x, the negative will just go away because you have all these squares, right? So negative x squared plus 1. And I think there was even a square on there. If I'm not, no, there's not. Okay, I'm mistaken. So the x squared times negative x squared is x squared plus 1. And you see that's exactly f of x. So therefore this thing is even. Okay, so what does that mean to us? That means we can cut it in half and multiply it by 2 and have the same answer. Let me go ahead and distribute this. And that makes our work a lot easier because the second part of the first fundamental theorem of calculus, that f of b minus f of a part, the f of a will just end up being 0. Okay, so we'll have 2 times antiderivatives x to the 5th over 5 plus x cubed over 3 from 0 to 2. And then we have 2 times 2 times 4, 8, 16, 32 fifths plus 8/3. And then minus 2 times what? Well, 0, right? So you plug in 0, those will both be 0. And then that'll equal 2 times, I guess I'm going to multiply both top and bottom by 3, so 96 fifteenths plus 40 fifteenths, and then 96 plus 40, 136. 2 times 136 over 15. 136 times 2, 12, carry the 1, 6, 7, 272. 22/15. Okay, it's still a lot of work, but it's easier if to cut it in half, because otherwise I would have had to put -2 in there and figured the whole thing out again and then subtracted all kinds of fractions. It's just been a nightmare. So anyways, there's kind of the spiel for U substitutions. Probably one of the most important tools you'll learn. So yeah, let's leave it at that, and I'll thank you for watching, and we will see you next time.